For thousands of years, humanity relied heavily on a metal that seemed to effortlessly solve practically every engineering problem we threw at it. Seriously, think about it. It was incredibly easy to dig out of the earth, ridiculously easy to melt, and you could shape it with almost zero effort. It resisted corrosion surprisingly well, and it was even dense enough to stop radiation in its tracks. For a huge chunk of human history, those specific physical properties made it look like the ultimate, totally perfect material. But, as we all know now, it was hiding a dark, incredibly toxic secret. Welcome to this explainer on the strange, fascinating, and honestly quite devastating story of lead.
So what actually happens when your absolute perfect building material turns out to be toxic? How on earth did humanity deal with that massive contradiction? Well, for centuries, we kind of just ignored the second part of that question and put this stuff absolutely everywhere. We literally built entire societies on top of it, completely altering our environment in the process. Today, we're going to unravel this material as one connected story. We'll explore how we found it, how its atomic structure creates those amazing properties, and how we eventually had to reckon with the heavy consequences of using it so widely.
All right, let's dive right into this. Lead is a heavy metal sitting right there on the periodic table as atomic number 82. Now, you almost never just find pure, shiny, metallic lead sitting around in nature. It's usually bound up chemically with other elements, buried deep underground. Its most common natural ore is a mineral called galena, which is mostly just lead sulfide. Galena has this really striking dark metallic look to it, and crucially, it is just packed with a super high concentration of lead waiting to be extracted.
You know, if you've ever stared at a periodic table in chemistry class, you might have wondered why the symbol for lead is Pb. I mean, it doesn't even have a P or a B in the name. Well, that comes straight from its Latin name, plumbum. And what's really wild is that this exact Latin root is where the English language gets the word plumbing. That fact alone really tells you everything you need to know about how deeply intertwined this metal was with ancient Roman water systems. They absolutely loved the stuff.
To really grasp why ancient engineers were so obsessed with lead, you just have to compare it to something like iron. Pure lead is phenomenally dense. We're talking about 11.34 grams per cubic centimeter. So a block of lead is about 1.5 times heavier than the exact same size block of steel. But here's the real game changer. Lead melts at a shockingly low 327 degrees Celsius. Think about a regular roaring campfire. That is literally hot enough to melt lead. Iron, on the other hand, stubbornly demands over 1,500 degrees just to melt. For ancient builders, lead was basically a miracle. You didn't need crazy ultra-hot furnaces to work with it. Simple, everyday equipment did the trick perfectly.
And because of that super low melting point, manufacturing it was incredibly straightforward. Transforming it from raw rock to useful metal is essentially a quick three-step process. First, you mine that galena ore we talked about. Second, you heat it up, a process called smelting, which chemically drives off the sulfur. And finally, step 3, you are left with heavy, pure metallic lead. Because getting the ore was so easy and the smelting was basically effortless, lead quickly became one of the very first metals humans ever mass-produced.
Since it was so remarkably easy to make, lead basically became humanity's permanent go-to solution whenever a new engineering problem popped up. The ancient Egyptians, they used lead compounds to make pigments and cosmetics. Then the Roman Empire comes along and uses mind-boggling quantities of it to seal joints, line their roofs, and cast thousands of miles of piping for their massive plumbing infrastructure. Skip ahead to the 19th century, and we're harnessing its unique chemistry to invent the lead-acid battery. By the 20th century, we're literally pouring it into our gasoline to stop engine knocking. Over and over again, lead was the silver bullet.
Section 2. Chemistry to application. Okay, to really understand why lead kept saving the day, we need to zoom way in. We have to look at the microscopic level to see how lead's specific atomic structure creates its physical properties, and exactly how those properties dictate its real-world application.
This perfectly illustrates the golden rule of materials engineering. Chemistry dictates structure, structure dictates properties, and properties dictate applications. It is a direct pipeline. Because lead has a very high atomic number, meaning it has lots of electrons and super heavy nuclei packed close together, it's incredibly good at absorbing and attenuating photons. That property makes it the ultimate medical X-ray shield. Because its atomic lattice is unusually soft, the metal is highly malleable. It bends without cracking, which made it perfect for Roman pipes. And because it happens to undergo completely reversible electrochemical reactions with sulfuric acid, it can store and release electrical energy, making it the bedrock of battery tech.
But speaking of batteries, that introduces a really fascinating modern engineering paradox. Think about this for a second.
If lead is so exceptionally heavy, and its energy density is honestly pretty terrible compared to modern lithium-ion tech, why is there still a chunky lead-acid battery under the hood of almost every conventional car today? Why hasn't this heavy, outdated tech just gone extinct?
Well, the answer is that materials engineering is literally always a game of trade-offs. It's rarely just about saving weight. When you turn the key in your car, the starter motor needs a massive, instantaneous burst of electrical current to get going. Lead-acid batteries are uniquely fantastic at delivering that huge jolt. Plus, they're relatively cheap to make, the technology is fully mature and incredibly reliable. They can survive the freezing and boiling temperatures under your hood, and, maybe most importantly, we already have a massive, highly efficient recycling infrastructure built for them. For that specific job, lead is still really tough to beat.
Section 3. The toxicity crisis. So for thousands of years, humans were practically patting themselves on the back for all these amazing engineering wins. But eventually, the biological reality of surrounding ourselves with this metal finally caught up with us.
Here is the harsh, undeniable biological truth. Lead has absolutely no known beneficial role in the human body. Zero. None. Once it gets inside us, it just wreaks havoc across multiple organ systems. And the danger is especially devastating for children because their developing nervous systems are exquisitely sensitive to it. What makes it so utterly insidious is that lead doesn't even need to cause immediate dramatic symptoms to ruin your health. Just chronic, low-level exposure over time causes severe, totally irreversible damage. And there's really no historical event that highlights this brutal conflict better than the invention of leaded gasoline. See, early car engines had this nasty issue called knocking, where the fuel would combust at the wrong time. Engineers discovered that mixing a specific compound called tetraethyl lead into the gas brilliantly fixed the problem. Pure engineering success, right? Well, from a public health standpoint, it was a global catastrophe. Burning that gas essentially turned millions of cars into mobile toxic waste emitters, spraying invisible lead pollution into the air, the soil, and our lungs all over the planet. And man, gasoline was far from the only culprit. Historically speaking, we managed to hardwire a terrifying number of exposure pathways straight into our daily routines. We had lead water pipes leaching directly into our drinking glasses. We painted our walls with lead-based paint, which eventually dried, flaked off, and created toxic dust right in our living rooms. We shot lead ammunition that poisoned our soil and local wildlife. Factories pumped into the sky, and we even ate off ceramic plates with lead glazes that seeped into our food. We literally boxed ourselves in with a persistent poison.
Which leads us to a really sobering concept in material science known as material legacy. You see, a harmful material doesn't just vanish the second a government passes a law and engineers stop using it. Because lead is so incredibly durable and resists breaking down, it just stays there. It lingers inside our old buildings, it's buried in our underground infrastructure, it's trapped in our soil, and it flows through our waste streams for decades, sometimes centuries. Lead has burdened humanity with one of the absolute largest and most hazardous material legacies in the history of industry.
Section 4. The ultimate engineering lesson. So, how are we supposed to handle all of this today? We obviously cannot rewrite history, but we have fundamentally changed our strategy to cautiously manage the lead we do still use, rather than just banning it completely across the board. The way we mitigate the risk today is through strict, closed-loop systems, like what we do with car batteries. You drop off your old battery, it gets collected, safely broken down, the lead inside is melted and refined, and then it goes right back into a brand new battery. When lead is tightly sealed inside a controlled industrial loop with a good recycling program, it has a completely different risk profile than lead getting sprayed out of a tailpipe or flaking off your bedroom ceiling. The chemical element is exactly the same, but the pathway into our bodies is totally cut off.
And that brings us to the ultimate takeaway here. A good engineering material isn't just one that gets the job done. It has to get the job done while its entire interaction with people and the environment is fully understood and rigorously controlled. Lead forced us to learn that lesson the hard way. It proved that you just cannot judge a material on its short-term usefulness. You have to anticipate its entire life cycle, from the moment you pull it out of the ground to the moment you throw it away. Which honestly leaves us with a pretty unsettling question to wrap up this explainer. It is so easy to look back at the Romans or those mid-20th century automotive engineers and wonder how they could have possibly been so oblivious to the dangers of lead. But as we continuously invent and adopt brand new miracle materials to solve today's big problems, we really have to look in the mirror and ask, what perfectly useful, completely normal materials are we building our world with today, right now, that are destined to become tomorrow's toxic legacy? Thank you so much for exploring the incredible complex story of lead with me in this explainer. Always keep questioning the world around you.